guys, in today's video we'll look at what are carboxylic acids, their properties, the solubility of our carboxylic acids, reactions they undergo, including reactions with metals, metal oxides, metal hydroxides and metal carbonates, and finally we'll look at an exam style question.
So what are carboxylic acids? Well, we've met them plenty of times before when we talked about the oxidation of our primary alcohols and our aldehydes. Our carboxylic acids contain this functional group here, this COOH functional group. And you can see you can almost break it down into two separate parts. We have this carbonyl group here, the carbon double bonded to an oxygen, and we also have this hydroxy group over here, this OH group over here. Now, the way we name our carboxylic acids is that we have an oic acid in the ending, and then the carbon chain will be the prefix. Now, the carbon in the functional group is included in part of the carbon chain when we're looking at straight chain or branched chain carboxylic acid. So, for example, if we look at this molecule here, you can see we have one carbon involved, so this is methanoic acid. If we look at this example over here, we have 1, 2, 3 carbons, so this is propanoic acid. So we're using those principles of naming our organic compounds, which we learnt in a previous video, and applying it to our carboxylic acids. Now, the carbon in the functional group is counted as the first carbon, and that's very useful when we're looking at branched chain carboxylic acid. So you can see if we had 1, 2, 3, 4 carbons, the first would be the one over here in the COOH functional group. So that makes this molecule 3-methyl butanoic acid. Butane because there's 4 carbons, 3-methyl because there's a methyl group on the third carbon. However, there is one notable exception to this. When our COOH group is attached to benzene, the carbon in the functional group is not counted in the root. So you can see here we have a benzene ring with a COOH attached to it. This carbon is not in the functional group and therefore not counted in the root. So the root is benzene and it's benzene carboxylic acid. You can see the formula is C6H5COOH. So now we have a good idea what carboxylic acids are and what they look like in terms of their formulae. Let's have a look at the properties. The first property we're going to look at is the solubility of our carboxylic acids. Well, short-chain carboxylic acids are soluble in water, and that's because they can form hydrogen bonds with the water molecules. If you have a look, in red I have drawn the simplest carboxylic acid. This is methanoic acid, and you can see that our carbonyl group, which we know has that slight difference in electronegativity where the carbon is slightly positive and the oxygen is slightly negative, and we know that our hydroxy group has a similar difference in electronegativity with a slightly negative oxygen and a slightly positive hydrogen. So what we have is 3 polar bonds, and the presence of this OH bond over here, or OH group over there, means that our carboxylic acids can actually form hydrogen bonds with water. Now, as the carbon chain length increases, the solubility decreases. So it's the short chain carboxylic acids that are most soluble. Now, if we have a look at the boiling temperatures and the trends that we see in these. Well, hydrogen bonding can actually occur between our short chain carboxylic acids, as you can see here. You know we have those 3 polar bonds, and we have a hydrogen over here, and we have an oxygen attached to an electronegative carbon, which allows these hydrogen bonds to be formed. Now, when 2 molecules are identical and they form hydrogen bonds with each other, we call this a dimer, and we say a dimer is formed. So, for example, if you look at what I've drawn here, if we had a hydrogen here and a hydrogen here, each of these carboxylic acids would be methanoic acid, and this would be a dimer with 2 methanoic acid molecules joined together. Now, in general, our carboxylic acids have a high melting point, and it's higher than comparative alkanes. Now, London forces actually increase as the carbon chain length does, and that's why we see a trend that the boiling point will increase with molar mass. So our carboxylic acids also have a distinctive smell and taste. One of the most interesting ones is butanoic acid, which has a distinct vomit smell. Now, they're also a weak acid. They partially ionize. they release these hydrogen ions to form a carboxylate ion, and you can see that over here. Remember, it's only a weak acid, so it's a reversible reaction. You can see we have our general formula over here for a carboxylic acid, and it's becoming partially ionized to form this carboxylate ion. And if we take a closer look at the carboxylate ion, so here I've drawn our general formula for our carbox. So here I've drawn our functional group, our COOH functional group, and I've labelled on those dipoles as well. And you can see those 1, 2, 3 polar bonds. So it's a weak acid, it's going to become ionized and lose this hydrogen over here. And what we form is we form this carboxylate ion. Now, interestingly, what happens is, in our carboxylate ion, the charge and character of the double bond that existed over here is distributed over both oxygens. And that's because these two bonds here and here are now identical. And we can represent the fact that the bond character and charge is represented over both of those oxygens, is distributed between both of them by doing this sort of dotted line and showing a negative charge between them. So let's have a look at some of the most simple reactions of our carboxylic acids. So our carboxylic acids will react just as you would expect acids to. We know it's a weak acid, so the only difference in its reaction is that it's going to react slower than strong acids such as hydrochloric acid. So carboxylic acids do indeed react with metals. And they'll react with metals above hydrogen in the reactivity series. They react to form a salt and hydrogen gas, and you'll observe an effervescence of a gas, which in this case is hydrogen. So the name of our metal salt involves the acid, where we change an OIC to an 8, and you'll see that in this example over here. I'm going to use methanoic acid for all of our examples just to keep it quite simple. So you can see we're reacting methanoic acid with potassium. And what we form is we form this metal salt over here, which is potassium methanoate. And you can see how we're naming that salt right now. We're also forming that hydrogen gas that we talked about, and we'll see that effervescence a bit. So let's move on to our next reaction. We're looking at the reaction with metal oxides. So just like acids do, carboxylic acids will react to form a salt, a metal salt, and water. So here we again have our methanoic acid. This time we're reacting with sodium oxide, and we form sodium methanoate, and we form some water as well. Now let's have a look at the reaction with metal hydroxides. Well, they react to form a metal salt and water, and this is actually a neutralization reaction. You can see again we have our methanoic acid. It's reacting with sodium hydroxide, and it's reacting to form sodium methanoate and a water molecule. The last reaction we're going to look at is the reaction with metal carbonates. Our carboxylic acids react to form a salt, water, and carbon dioxide. Here you can see we've got methanoic acid reacting with sodium carbonate to form sodium methanoate, water, and carbon dioxide. Now they will also react with metal hydrogen carbonates in a very similar way. Now there's just one thing I want to quickly cover. The salts we mainly looked at today were sodium and potassium salts, but you can get a magnesium salt as well. But it's important to note that magnesium has a 2+ charge on its ion. So when you form something like magnesium methanoate, you're going to have 2 of our carboxylate ions. And that's incredibly important. If you miss that out, you really haven't got the right formula. So just remember that when you are doing your equations that involve magnesium with our carboxylic acids. So let's have a look at an exam style question together. Carboxylic acids are weak acids. Explain the term weak when applied to acids. Write an equation for the reaction of ethanoic acid with sodium carbonate. And benzene carboxylic acid, C6H5COOH, is a carboxylic acid where the R group is a benzene ring. The dissociation constant, Ka, for benzene carboxylic acid is 6.31 times 10 to the minus 5 moles per decimeter cubed. Write an expression for Ka for benzene carboxylic acid and calculate the pH of 0.01 moles per decimeter cubed solution of benzene carboxylic acid and give your answer to 2 decimal places. So the first 2 parts of the question are relatively simple. We're talking about what weak acids mean. Then we're asked to write an equation for the reaction of ethanoic acid with sodium carbonate, our metal carbonate, which we know we can do. We learned that today. And then this third part of the question is reminding us about working out pHs and acid dissociation constants. So that might require a little bit more thinking, a little bit of revision, but let's work through it together. So for the first part of the question, you can see we've answered by explaining that weak acids are only partially ionized. So now let's move on to the second part. You write an equation for the reaction of ethanoic acid with sodium carbonate. Well, ethanoic acid looks like this. We have 2 carbons. We'll have that carboxylic functional group over here, and we'll have our 3 hydrogens over here. So the formula would be CH3COOH. Now we're reacting that with sodium carbonate. That's Na2CO3. We're going to form a salt, and we know that salt is going to be sodium ethanoate, and the formula of that is going to be CH3COONA. I sometimes find it quite helpful to actually draw out the formula with the bonds included when we're doing things like this, when we're doing these type of reactions, because then I can see where our sodium is bonded onto. So let's fix our equation by adding on the remaining products. We've got some water and some carbon dioxide, because we know those are the products formed when we react our acid with our metal carbonate. Now it's just a matter of balancing. Immediately I can see we've got 2 sodiums on the left, so we balance that with a 2 over here. Now we've got 2 carboxylic ions, so we need to balance that with a 2 over here. And we can see that's a well-balanced equation. So now to move on to the slightly trickier part 3. To write an expression for the Ka, the acid dissociation constant for benzene carboxylic acid. So the first thing I'm actually going to do is I'm going to write out the equation for the dissociation of benzene carboxylic acid, because I think that will help me. So we have C6H5COOH. And we know our carboxylic acids are weak acids, so it's a reversible reaction. And that's going to dissociate to C6H5COO minus plus H plus. Now we know that when we're writing the acid dissociation constant, we're going to have H plus A minus over HA. So if I fill those in, we've got H plus, and then our A minus is this over here, so it's C6H5COO minus, all over HA, which is C6H5COOH. There we go. So now we're going to use that, and we're going to calculate the pH of a 0.01 mole per decimeter cubed solution of our benzene carboxylic acid. So the first step that we're going to do is we're going to write down the assumptions that we're making. And we know that there are special assumptions made when we're working out the pH of a weak acid. The first is that the concentration of hydrogen ions is equal to the concentration of A minus. So in this case, the concentration of hydrogen ions is equal to the concentration of C6H5COO minus. The second assumption we're making is that the initial concentration of HA, so HA initial, let me write that correctly. The second assumption we're making is that the initial concentration of HA is equal to the final concentration of HA. So that's C6H5COOH beginning is equal to C6H5COOH final. So now we can slightly change around our expression that we've made up here. We can write Ka is equal to H plus squared over the concentration of C6H5COOH. Now we want to work out the concentration of hydrogen ions first, so we can again rearrange that equation a little bit further, and we'll see that we can get the concentration of hydrogen ions squared is equal to Ka multiplied by the concentration of C6H5COOH. And you'll see we're actually given both these values in the question. If I scroll up, you can see that the concentration of our benzene carboxylic acid is given over here, 0.01 moles per decimeter cubed. And we're given the value of Ka over here, 6.31 times 10 to the minus 5. So we can go ahead and we can substitute in those values. Ka is 6.31 times 10 to the minus 5. And our value for the concentration of our benzene carboxylic acid is 0.01. So you can see the concentration of hydrogen ions squared, it's important not to forget that squared, will be 0.000000632. So now we know the concentration of hydrogen ions squared, we can take the square root of this number to find out the concentration of hydrogen ions. So that would be 0.00079498427. Now, as the final part of the question is asking us to round, I haven't rounded anything yet. I've kept my numbers nice and large. The rounding can be done in the last part so as not to lose any accuracy. So now we know the concentration of hydrogen ions, we can work out the pH, because we know that pH is equal to the negative log of our concentration of hydrogen ions. So we're going to take the negative log of 0.00079498427 and take your time not to mistype any of these numbers because it'll give you a wrong answer. And we find that pH comes out to be 3.099, and we are actually asked to give this to 2 decimal places. So if we round this to 2 decimal places, you can see that it's 3.10, and that O is incredibly important. Without the O, it's not 2 decimal places. And we can write 2DP. So there you go. We've answered really what is quite a long and tricky question. We've ensured that we've explained what we're doing as much as we can on paper for our examiner to see. We've laid out all the steps and equations that we're using. So let's summarise what we've learned today. Carboxylic acids have a COOH functional group. You can break that down into a carbonyl group and a hydroxy group. The R group can be a hydrogen, an alkyl chain, or a benzene ring. The solubility of our carboxylic acids. Well, the molecule contains 3 polar bonds and it's actually able to form hydrogen bonds with water. This makes these short chain carboxylic acids soluble. The solubility decreases with increasing hydrocarbon chain length. The boiling point of our carboxylic acids. The molecules can form hydrogen bonds together, and if the molecules are identical, a dimer is formed. As the chain length increases, we see an increase in the London forces. This allows for an increase in boiling point, and boiling point will increase with molar mass. In general, we see a higher boiling point than of comparative alkanes. Our carboxylic acids have a distinctive smell and taste. It's very distinctive. The carboxylic acid is a weak acid. It's only partially ionized in water and it forms a carboxylate ion. This carboxylate ion is formed through the loss of an H+, a hydrogen ion. Now, it involves 2 carbon to oxygen bonds, and these are identical. The charge of our double bond and the charge and the character of our double bond is distributed across the 2 carbon to oxygen bonds. If we look at the reactions of our carboxylic acids, they react as acids would typically do. They react with metals to form a metal salt and hydrogen, with metal oxides to form a metal salt and water, with metal hydroxides to form a metal salt and water in a neutralization reaction, and with metal carbonates to form a metal salt with water and carbon dioxide.